All right, let's see if we can do number 38 on 20.2.
Why is it y plus?
Positive axis.
Yeah.
It's upward.
Okay, so I want to calculate a circulation integral, right? Where f is x plus y, comma y plus 2z, comma z plus 3x. And the curve I want to calculate around is the boundary of a square of side length 7 in the xz plane oriented counterclockwise when viewed from the positive y-axis. Okay. So, thoughts?
I don't remember that other question being part of the.
You could do the greens here, right? Because you're in a plane.
Yeah, I'm in a plane. I could maybe think about applying greens there.
This isn't very easy.
Yeah, I've got to fiddle something a little bit, right? And that my vector field f includes 3 variables, right? But maybe we could fiddle that around.
Well, we can still get a 3-dimensional normal vector.
Yeah, we can still get a 3-dimensional normal vector, right? We could dot it. That would work. What the heck? Let's try it, right? So I think we'll see if we try. Wait, what would we try? We might think about trying greens, right? Or Stokes. I think if we try Stokes, I think we'll see greens in it. Let's see if we can find it, right? That'd be cool. So I've got a circulation integral. Why am I thinking greens or Stokes?
Because calculating circulation.
If we try to calculate a circulation, right? Greens or Stokes do that. It's a closed curve, right? And they told me C is the boundary of a square of side length 7, right? That means I'm going to have to, what?
Triple.
I'm going to have to do 4 things, right? If I was going to calculate the circulation by hand, I'd need 4 pieces for this.
Yeah.
Okay, see that? Yeah, if I don't want to parameterize 4 things, maybe I can just calculate an area integral and do it with 1 thing. Okay, see that? All right, so what do I start with?
If you're going to do Stokes, you'll need the curl.
Okay, if I'm going to do Stokes, I need the curl of f. Okay, so I better do that. So curl of f, how do you calculate curl of f? Okay, take nabla, cross it with your function f. Okay, let's see, so that's going to be the determinant of I, j, k, and who's in the middle? The partials. Partial with respect to x, partial with respect to y, and partial with respect to z.
X plus y.
Perfect.
Y plus 2z.
Good.
And z plus 3x.
And z plus 3x. Cool.
0.
Let's
2.
see. So I get on the i's
0 minus 2.
0. Oops, i's 0 minus 2. Cool. And then I got minus. What do you got in the j's?
3 minus 0.
3 minus 0. And k's? Oops. K's?
0 minus 1.
0 minus 1. Good.
So in total we get negative 6.
So all told, careful. I got negative 2i minus 3j minus k, right?
Oh. Okay.
Which is categorically a vector, right? Not a scalar. So I get the vector negative 2, negative 3, negative 1. You guys cool with that?
And that's
Okay.
the curl of that.
Yeah, perfect. That's the curl of f. Okay, so why did I do that?
Because we're gonna integrate the curl over the area.
Okay, I'm going to do the integral over the surface, right, of the curl of f dot the area.
And since the curl is constant, right?
Okay.
Can we just multiply that by 49? Oh wait, no, this isn't a scalar curl.
Yeah, this curl is a vector, right? So I need to find some, maybe let me write it this way
Oh,
first.
normal vector.
Let me say I've got the integral over s of this thing, -2, -3, -1, and I want to dot that with something and do a deregular area, right? What's the something I need to dot with here?
Normal would be
Negative.
Yeah, a unit normal. So what's your unit normal to the square of side length 7 oriented counterclockwise?
X, just J.
You guys see that? It's either j or minus j, right? It's a square of side length 7 in the xc plane, right? So it's sitting flat in the xc plane. Perpendicular to that, it's going to be something that sticks out along the y-axis one way or the other.
And j is going to be positive because we know y is positive.
Perfect. So if I look down from the y-axis, I see it counterclockwise, right? That means I'm looking down the normal vector. So my normal vector has to be 0, 1, 0, right? J. Okay, see that? Which is already unit length, right? So I don't have to adjust. So out of this thing, I get the integral over my surface S of -3, the area. And what's that? How big is the surface? How much area does the surface have?
49, so on the surface.
Square, 7 on a side, and it's flat in there, so
49 times
49. So I got negative 147. So what does that mean? What did I start this off calculating?
Calculating the vector.
Circulation.
Oh, circulation.
Yeah, remember they asked me for a circulation integral, right?
Oh,
Okay.
And so how did I get from a circulation integral to some frickin' curl integral?
So the eddy, the area.
Okay, yeah, I looked at, okay, the sum of this, or this total circulation, right? The amount this thing helps me get around that circle, or in this case, square, right, loop, is the total eddying in there. That's Stokes.
How'd you get the -147 times?
Oh, from here? So this is this guy here is the integral over surface, sorry, is -3 times the integral over surface the area. This stuff is just the area of surface. And I had my surface is a square of side length 7.
Yeah, because the integral of the
So the total area. Yeah.
So it just becomes
You guys see that? So where's greens here? Because I probably could have done this with greens. You guys see it? Yeah, I could have done this with greens.
I thought that would only
Well,
be
we only
when
have-
it's flat, though.
It is flat though.
Z doesn't matter, so we can just do the variable switch.
How about right here? See, I dotted this thing with 1.
Uh-huh.
Right, so I was actually only ever interested in this component. Where'd that 3 come from? That 3 came from right here. That was the J component from the curl.
Yeah.
You guys see that? And the J component out of the curl is the partial with respect to x
And then minus the partial with respect to
of
Z.
the last, so if these are P, Q, and R, I did the partial with respect to x of R and subtracted the partial
With respect to Z.
with respect to z of p.
Yeah, I see that.
You guys see that?
First and the last one.
Yeah.
And then there's a minus sign on there because adjustments need to happen, right? Would I have seen the minus sign if I had tried to apply greens? Maybe. Maybe not. You guys see that? I think it was probably important to try to apply Stokes here. Just to make sure I got everything exactly right up to minus signs. I think if I had just tried to cobble together greens, I maybe would have missed a minus sign. And also I got a little lucky, right? This guy didn't have any Y's in it when I was done. That guy didn't have any Y's in it when I was done. I got this kind of nice constant, right? If this constant had depended on Y, it would have maybe been a little bit of thinkiness.
So is it just generally better, even if it's overkill, to just do Stokes?
Yeah, the thing is Stokes is going to work regardless, right? Even if I happen to end up doing greens in some funny way, Stokes is the go-to. Unless greens fits right in there, I'd go to Stokes.
Also, I can't really visualize how you got the 0-1.
This guy?
Yeah.
Okay, so for that guy, right, I've got, forget this. We say this is the XZ plane, right? I've got a square of side length 7, right? It's living in the XZ plane, right? And it's oriented counterclockwise when I look at it from the positive y-axis. So I'm out here looking down the positive y-axis at this thing, and it's counterclockwise, which is what I like to see, right? So I know that the thing that points out at me is the normal vector. So that the normal vector out of there is the one parallel to the y-axis, which is something like this, 0, number 0. And I know that I need it to be like 1, so I normalize it to get j.
Okay.
Yes.
You guys cool with that? If you want to see greens from Stokes, you end up doing the same thing where the normal vector is k. Cool?